It's a pleasure and an honor to welcome our CEO, founder, and people, technology, and fearless leader, Dr. James Truchard.
Thank you. Thank you. Thank you for joining us today as we share our vision for the future for instrumentation and control applications. We feel there's some major influences that are changing the way we look. We've been developing these over the years. We've been watching as engineering has advanced, and it's a very exciting time for engineering. So it's good to be here in Germany to share some of our thoughts about it. So I'll start out with a simple example to kind of show our approach to solving engineering problems. So I'll start out with a question. One of the earliest known watches was back in 1530, and now we've used the watch for years. So how many of you are wearing a watch like this today? A lot of folks, right? And how many of you have the alternative watch? So we carry two watches now often, right? Like I do. Huh? Okay, so the fact is that we've created a platform in the form of this new kind of watch that does a lot of different things. So I want to put that in perspective of National Instruments' position in the marketplace. You know, how can we be doing instruments and embedded systems at the same time? Well, if you look at the applications that the iOS or Android do, you'll discover that they're doing both instruments and replacing physical embedded systems that we see here. So whether it's a thermometer or level or recording device, or one that I find very fascinating, a bagpipe tuner. You know, I didn't know a bagpipe was tuned, but I was at an event and there was a guy walking around with this tuner, and everybody was adjusting their pipes so that they get the right sound. So there is that. So I was curious, was there such an app on the available for the iPhone? Sure enough. Now I understand there's multiple apps. The one I saw at that time was $25. So whoever was making that bagpipe tuner has a big problem, right? There's now an app that runs on the iPhone that does the same thing from somewhere from $1 up. So basically, a platform fundamentally revolutionizes the way we operate and what the marketplace is in competitive nature. At the same time, while we have the instruments on one side, on the other side, we have the embedded systems. So one platform doing both. And if you go to the App Store and look, do they put instruments separate from embedded systems? No, they're all mixed together. So in fact, you have a platform that's doing both. And so the iOS creates this basic platform. We like to use this hourglass representation in line with our next speaker, which you hear a lot more about, this hourglass idea of a platform where you have the applications at the top. Literally, in the case of the App Store, 1 million applications, and then the integrating platform, and then the choice of hardware that you get to run that application on. So this concept of a platform is a very important one, and understanding how you can be about instrument or an embedded system. And the better that platform works, the more volume it achieves, more scale it achieves, and more ability to have the technology to create a very high level of differentiating at a very good price. So that's what platforms are all about, and our view of the platform is very similar, where we're literally solving hundreds of thousands of test and measurement applications and tens of thousands of embedded systems doing everything from, as you saw on the screen earlier, launching rockets into space, to robotics, to wind turbines and smart grid, and as well as all the traditional test and measurement applications, all in one platform, all with one point of view, with literally hundreds of or millions of possibility of what you can do with it, creating ever more efficient, taking advantage of Moore's law as we go forward, creating choices of hardware that match physically what you need for a specific application. So now, going back 3 decades in the history, this is a slide from 1983 that showed our vision of what we were going to do with instrumentation systems. At this time, we were making GPIB interfaces, but we'd come from the University of Texas, where it built a very advanced computer-based with A to D converters virtual instrumentation system. So we had this vision of a new way of looking at systems and test and measurement systems. And here we see some of the goals that we had at that time and some of the advantages we will want to build on. And over the last 3 decades, we've done it with GPIB, you can say it's reference 1, then moving to PXI, we could get 10 times the performance. And now in our FPGA-based approach, we get as much as 200 times the performance of a traditional GPIB system by taking advantage of ever-improving technology. So it was on this vision that we got to where we are today. So if you look at instrumentation, I started work in university where we had vacuum tube instruments, so like General Radio was a key player in the era of vacuum tubes. The instrumentation industry took advantage of transistors and integrated circuits, and a new vendor came to the fore in Hewlett-Packard. And now, as we see with the iOS and Android operating systems and the PC operating systems, that we have, again, a shift towards software. And in the software realm, the instrumentation, National Instruments has taken a leadership role in providing the technology that would allow us to build this instrumentation systems. Now, we've used this phrase virtual instruments, as we see in VIP, to show our vision for this software-based instrumentation, where we have a software view and a hardware view, which we've termed in terms of bits of resolution and sample rate. Now we've done RF, where we do down conversion, and taken advantage of Moore's law. And Moore's law is driving not only processing power, but our analog to digital conversion technology. Virtually daily, there's a new part available in the RF realm to make ever better performance in how we can build our systems. So we build on that technology. We leverage it to build our platform to give the most competitive solutions. So if we look at our vector signal transceiver, which we introduced last year, and we're introducing some extensions this year to it, where we got a comprehensive capability for measurements of RF applications, including those used in smart mobile devices, the new car with the integrated telecommunications capability. But we also can build, not only can we do tests, but we can also build software-defined radio in the same platform with literally thousands of apps available to add in and add on to do a variety of things like channel emulation and the like. So just a very advanced capability, all in one platform, building on generally available off-the technology, typically base station technology now, to create a capability that we haven't seen before. So this is a state-of-the-art example of our approach here. And what we've done now is combine the ability to program both multi-core processors and FPGAs in the way that we get the performance we need to replace what would have been custom design instrumentation. So basically, we're able to give hardware level performance with our software in a key point. Another area that we're working on going forward is distributed computation and distributed systems that we can work in the same environment in the same way. So that's really our goal, is to bring that technology available in a very accessible way across literally millions of applications. So how does this fit in the big picture and one of the major trends? If we look at the Industrial Revolution, the first revolution is when you could go beyond manpower and use water and steam power to run machines. The second one was about electrical power being applied to be more ubiquitous and provide mass production. In the third industrial revolution, we added electronics, the PLC, SPS, as we call it here, was invented to go to the next level of automation, with electronics included. Now, we're here today talking about the fourth industrial revolution. And there's a working group here in Germany called Industry 4.0 that's working on this. And we use the phrase cyber-physical systems. In other words, this generally available or ubiquitous availability of information that can be integrated into a decision process anywhere in the value chain, all the way from the upfront measurement, say, to the end decision-making process. So with this, you see it around you every day. You know, information is just so available. We use our phones for GPSs and the like. All these things are converging in a way of tremendous access. Cyber-physical systems enable the physical world to merge with the virtual, leading to the things we hear about every day. Internet of Things, data and services. So computation, communications, control are some of the key elements of this. Here's some phrases that are used: the programmable world, Internet of Things, intelligent systems, Industry 4.0, smart factory, machine, all terms trying to capture this concept, that all the convergence of all this ability to understand and know what's going on. We use the term big analog data solutions, you know, being in the data acquisition business, measurement business, of course. Now we're accumulating tremendous amounts of data. Well, what if we could take that data to the next level and get information from it that's widely available to all the folks who people who care about that information? So basically, that's some of the things that we're looking to do and want to be a part of. Here's from an initiative of the Office of Science and Technology out of the United States White House, talking about cyber-physical systems and their a role in how we see in the future go forward. So in our case, it's about graphical system design that's used to build these cyber-physical systems. You know, one of the phrases I use is that for the first time in history, we can have advanced measurements in the same platform we have advanced control. Again, so you're bringing all these elements together in a way that we use multi-core processing, FPGAs and the like, to create this advanced measurement and advanced control capability. So another phrase we use to do for cyber-physical systems what the PLC or SPS did for discrete control systems. Here's some of the examples we do, all the way from medical devices to next generation MIMO systems with OFDM, smart grid. We have a smart grid analyzer controlling some of the biggest physics projects on, like CERN, Large Hadron Collider, a large telescope, or simulating a train or robotic habilitation, and rapid control prototyping. A lot of different applications, all with the same platform. Now, the concept we brought out 5 years ago at a keynote at NI Week was this idea that big data has some importance beyond just what we would normally think of it. Big data is not just more, it is also different. So lots of sensor capability, lots of measurements, all coming together to create a new capability. And it's about changing data into information. So it's allows us to make much better decisions, use data you never thought of as really being important to get better use of energy, more efficient machines, lower carbon footprints and the like in how we operate. So if you look at it, where we started back when we started with our data acquisition, we thought in terms of one engineer, acquire, analyze, present. Now we think of it in terms of the overall system, all the way from data acquisition systems, measurement systems, control systems, all the way to the IT infrastructure. Products like our Diadem software designed to help us in this process, and we'll be moving those forward in things like machine condition monitoring and the many spaces where we can add value by turning the data into information. So we use the phrase big analog data, where we take the signals from sensors, and then we have our system nodes that do acquisition and the first level of analysis with the FPGA and multi-core processing, then move into the IT infrastructure for a more integrated way of making decisions. So one example I got to visit firsthand was in Dresden, where for the last 7 years they've outfitted some of their light rail cars with our compact Rio, and got like a 0.5 terabyte of data. And the students have written now 19 papers talking in a way that data can be made valuable. Things like how you run the car, so one car's going uphill, one's going down. You can minimize the voltage rise on the grid so that you can not have to use mechanical braking to save energy, how the tracks are tearing up the cars. All these things are integrated over time and turning this data into information about how to run your rails in a better way. So it's a nice, simple example, everyday example that really brought it home to me, the way data can make a difference. So here's some of the areas that we're working with big data. Of course, in MIMO systems, for example, you go out in the field and test how well your RF signal strength is. Well, that quickly accumulates tremendous amount of data. The smart grid, we know as we bring all kinds of energy sources on, and we have to figure out the best way to ensure that that energy can all be used. For example, again, data plays a big role with things like smart grid analyzer, like keeping the grid stable, and that is another example. Large telescope, I mentioned some big physics applications, and others that really taken this idea of use of data and turning into information. So for us, it's about graphical system design, using the platform to solve the big engineering challenges. You sometimes talk about the engineering grand challenges, where we're heavily engaged with our platform-based approach, where scientists and engineers can quickly deliver solutions to very advanced problems. So today, as part of this year's VIP, we're looking at how we equip engineers, we're looking at how we solve the grand challenges, and then we look to the future for the next generation, how we inspire them to love engineering, to do engineering, do all the things we know are so important to society to make this a better place to live.